Beth.
And I'm Beth.
Welcome to Physics with Beth and Beth.
Hello everyone, and welcome back to Physics with Beth and Beth. I'm Beth, and this is the second video of the first unit of our calculus-based physics curriculum. In this video, we're going to be talking about derivatives. And if you're taking calculus concurrently with your current physics class, you probably haven't talked about derivatives yet. But the thing is, derivatives allow us to talk about how things change over time, and that's really important in physics. So since we need that tool so immediately, we can't really afford to wait until you get to it in your calculus class. As a result, in this video, we're going to talk about an introduction of derivatives from the context of how you're going to need to use them in your physics class. Later on in your cal course, you'll get deeper into the nitty-gritty of them and talk a lot about the hows and whys of all the rules we're going to introduce today. But in this video, we're going to try and keep it short, simple, and sweet. All right, so in our last video, my fellow Beth walked you guys through the idea of how we can transform between position, velocity, and acceleration by taking the slopes of our position time or velocity time graphs. So velocity is the same as the slope of position, how position is changing over time. But what do we do if our position time graph is really gross looking, like a parabola, for example, instead of a straight line? Here we have a slope that's constantly changing. A great example of this would be an object in free fall. When an object first starts falling, it might have a velocity really close to zero. But then as it continues falling, it speeds up and goes faster and faster and faster. Its slope gets steeper and steeper and steeper as gravity accelerates it downwards. So how on earth do we find the slope of something when that slope is constantly changing? Well, maybe that's a little bit hard of a question to ask. Maybe we should ask a slightly simpler one. What about the slope of our line at just one point? If we can figure out how to find the slope of our line at exactly this point, then maybe we can extend that to talk about the slope of our line at all points. But let's just focus on one for now. Well, if I want to find the slope of my line, I just pick 2 points and I do rise over run to find the slope between them. So like say here and here, when my point is here. So I just say, well, what's my change on my y-axis? And I divide that by the change on my x-axis, my rise over run, my change in x over my change in time. And that gives me my average slope between those 2 points. Done. Except that's not quite what we were looking for, is it? We were looking for the slope at exactly this point, my instantaneous velocity when we were exactly right here. What this gives us is the average slope, averaged out over this whole big chunk of our line. So yeah, well, that'll be probably close-ish to our instantaneous velocity at exactly that point. That average velocity isn't going to be exactly the same. And sometimes in physics, we care a lot about being really precise and really accurate. If you're using physics to build a bridge, for example, you really don't want to mess up on these numbers. So, how do we make this a little more accurate? Well, maybe we could average over a smaller region. That would get us closer, right? So instead of picking 2 points that are super far apart, like here, I could maybe pick 2 points that are a little closer together and average between those 2 points. That would get us closer, right? But that's still not exactly what we were looking for either. It's still an average, and it's still not exactly precise. We could get a little closer, though, by moving our 2 points even closer in. But that's not exact either. That's still an average. So if I go a little closer in, that's closer, but it's still not exact. That's still an average. What I would really love to do is continue bringing these points closer and closer together until they're infinitesimally far apart. That would give us exactly the slope at exactly this point. I would love it if we could do that. If we could, and a mathy way to say this, take the limit of this as our points get closer and closer and closer together. Oh, but how on earth do we do that? That's such a bizarre question to ask, right? Thankfully, there is an answer, and that answer is a derivative. Derivatives allow us to find the instantaneous slope of functions at this point and at all other points by finding the slope between 2 points that are infinitesimally far apart. Instead of writing out all of this, though, we often notate derivatives by saying something like this. So instead of writing the limit of delta x over delta t, I can just write dx over dt, where this d means an infinitesimally small distance, or a differential. I can say this out loud by saying the derivative of x with respect to t, or dx over dt. Sometimes you might also see this written out as x prime of t, which you can say out loud as the first derivative of x with respect to t, or by just saying x prime of t. Both of these mean the same thing as this, and they're all different ways of talking about the derivative. But how do we calculate that derivative? Well, thankfully, there are a few rules that we're going to go into that allow us to quickly and easily find expressions for the slope of our line at all points. And the first one that we're going to introduce today is the constant rule. So if my position time graph is just a constant value, for example, something like x of t equals 5, let's switch to a different color that's a little more fun. If my position time graph is a constant, well, then I just have a straight horizontal line. Horizontal lines have a slope of 0, right? And the same way, the derivative of any constant is also going to be 0. So if I have a function where my position time graph is equal to a constant, then the derivative of that, or dx dt, is going to be equal to 0, no matter what this constant is. And also, just a quick aside, this doesn't only work for position time graphs, it also works for velocity time or acceleration time or anything you'd like. The derivative of anything will always follow these rules, no matter what it is that you're representing with your original function. Okay, so that's the constant rule. The second rule that we can use whenever we're trying to take the derivative of a function is the power rule. So the second rule is the power rule. And in general, it looks like this. If I have a function where I have my variable being raised to some exponent, so here I have t being raised to the nth power, and I take the derivative of that, then the derivative of that function is going to be my original exponent times my variable to an exponent that is 1 less than it was in the original. So we take this number that we're being raised to, we move him down in front, and then we subtract 1 from our exponent. So, for example, if I had a function that was x of t is equal to t squared, for example, and I took the derivative of that, then dx dt would be equal to 2, because I moved this exponent down in front, times t to the power of 2 minus 1, which is 1. Or in other words, just 2 times t. This rule always works anytime you have any exponent. And in fact, fun fact, it doesn't matter if you have a coefficient in front of this t when you start out. So if I had something along the lines of x of t is equal to 2 times t to the negative 1 power, I can still use the power rule. This constant being multiplied at the front doesn't affect anything. So all I do is I take my exponent, I multiply him down in front. In this case, negative 1 times 2 is negative 2. And then I subtract 1 from my exponent, and I get negative 2. So that's how you can take the derivative of any expression that has an exponent. And this also, quick aside, makes sense, because if we're thinking about our graphs of motion from earlier, if we have a graph of position that looks like a quadratic, for example, an object in free fall, then its velocity graph is always going to be a linear function, like this. So my object starts at a 0 velocity, and its slope gets steeper and steeper and steeper as time goes on, because we subtract 1 from the t squared in our quadratic expression for movement here. All right, so that's our second rule, the power rule. We have the constant rule, the derivative of any constant is always 0, and we have the power rule. If we have our variable being raised to an exponent, we can take the derivative of that by just multiplying that exponent in front and then subtracting 1. The sum rule tells us that we can take the derivative of each term in our sum independently and just add those derivatives together. A key word here is in a sum. If you have multiple terms with your variable in it being multiplied together, gross stuff starts happening and we ain't touching that yet. But for now, if you have different terms being added together, you can absolutely use the sum rule and just take the derivative of each piece independently. So, for example, say I had an equation that looks a whole lot like this one, just with values plugged in for x naught and v naught. So if I had an expression for x of t with an initial position of, say, 10 plus 3t plus 1/2 negative 10t squared, and I wanted to take the derivative of that, well, I can just take the derivative of 10, then the derivative of 3t, then the derivative of 1/2 times negative 10t squared, and I'm good to go. So, in this case, dx dt would be equal to what? Well, starting with the derivative of 10, 10 is just a number, it's a constant. So that would be a horizontal line. We can apply the constant rule, it would have a slope of 0. So its derivative would be 0. Okay, then plus 3t. Now, it might not look like it, but there's an invisible little exponent here that's really just a 1. So we can apply the power rule here. If I want to take the derivative of 3 times t to the first, then I just take my 1, I multiply him down in front, and then I subtract 1 from my exponent. So I'll get 3 times 1 times t to the 0th power. Now, any number being raised to the 0th power is just 1. So it turns out that this simplifies down to just 3. Then I have 1/2 times negative 10t squared. We're going to simplify that a little bit to negative 5 times t squared. And this is again just going to be the power rule. So I take my 2, I multiply him down in front to get negative 5 times 2, and then I subtract 1 from my exponent. So t to the 2 minus 1 power, or just t to the first. So why did I do negative 5 times 2? This is just going to be negative 5 when I take 1/2 of negative 10. That's just negative 5. So then I get negative 5 times 2. Oh no, I did that right. So then this is just going to be negative 10 times t to the first. So then the derivative of my expression, if I simplified everything down, would just be 3 minus 10t. Because I applied the constant rule here, the power rule here, and the power rule here. And that is a great example of all 3 of the basic rules that you're going to be using as you get started with the derivatives in your physics class. If you have any questions, please let us know in the comments, and happy physicsing!